Alright, folks, continuing here in Chapter 7. In Section 7.4, we're going to learn a new integration technique. It's called integration by parts. And it's kind of a little bit more difficult than integration technique than use substitution. What we're going to see is that for certain integrals where our previous techniques, such as use substitution, would not work, this technique called integration by parts might be the key to getting an antiderivative. So I'm just going to get on with it. I'm going to write down the integration by parts formula. I encourage you to read on page 544 the derivation of the integration by parts formula. That way you can see where it comes from, and you can see that it is kinda, sorta like a product rule, because it comes from the product rule for differentiation. But getting on with it, here's the integration by parts formula. For two differentiable functions, u and v, so you can think u is representing a function such as u of x, v is representing a function such as v of x. When you integrate u dv, the formula says the product, or the result of integrating u dv is u times v minus the integral of v du. So you're going to have to look at the original integral that you're given, and you got to look at the original integral and see what part of that original integral are you going to let u equal, and then what part are you going to let dv equal. It's going to be kind of like a double substitution. Once you decide what u is equal to, you must compute du. Once you know what you're going to let dv equal, you must compute v. Now, and to get v from dv, you're going to have to do a quick little mini integration problem. So before we look at an example, let me give you my guidelines for the selections of u and dv. So we're talking about the original integral, what we're going to let u equal, what we're going to let dv equal. So first, guideline number 1. You're going to select dv to be the most complicated part of the integrand that is easily integrated. Then u would be the rest. Or, guideline 2, you select u so that its derivative du is a simpler function than u. Then you're going to let dv be the rest. So right now, you might be looking at this and saying, what in the world is going on? I'm not quite sure I understood everything. Again, hopefully you have this in your notes, because as we go through a couple of examples, that's where this will start to make sense on what I'm talking about here. So let's look at this example. Determine the following integrals. A is the integral x e to the x dx, and b is the integral x e to the 2x dx. The integral in A is considered to be the most classic example of integration by parts. Every calc book written, any calc book you look at that's in existence, I would say the integral in part A is either the first or at least the second example in any calc book illustrating integration by parts. So let's head off to the chalkboard so you can see, how to break these down, to what you're gonna let u equal, what you're gonna let dv equal, and go through the process of integration by parts. And hopefully after a couple of these two examples, you'll say, hey, it's not so bad. And then of course I'll ask you to try one on your own. So make sure this is written down, because I'm heading off to the chalkboard. All right, in this example, we were asked to determine the following integrals. A was the integral x e to the x dx. B was the integral x e to the 2x dx. And I just told you that this is a classic example for the technique known as integration by parts. It's classic because it kind of fits both of those guidelines that I just went over with you. So let's crank this through integration by parts. I'll show you how I do it, how I suggest you do it, and how I'm using the guidelines. Okay, so I look at the original problem, the integral x e to the x dx. I notice that if I let u equal x, and then dv is the rest. So first, notice I am looking at the original integral as u dv. But I notice if I let u equal x, the derivative du is a simpler function. The derivative of x is just 1. So du is dx. And that was one of the guidelines. I also notice if I let dv equal e to the x dx, well, e to the x dx is the most complicated part of the original integrand that I can easily integrate. And why am I saying easily integrate? Because when you write down dv equals e to the x dx, in order to get v, so to go from dv to v, you have to undo that differentiation. That means you have to integrate. So you're really doing a little mini integral and going from here to here. Well, what's the antiderivative of e to the x dx? We know that that's just e to the x. And I'm not worried about putting on a plus c here. It's an indefinite integral. I'll just save the plus c to the very end. So I write all this down, and then I write down the original integral, and now I crank it through the integration by parts. So remember, the integration by parts says when you have the integral of u dv, it equals u times v. Well, u is x, v is e to the x, minus the integral of v, that's e to the x, du. du is dx. Almost done. Now you just have to integrate e to the x dx, which is very easy. You know that's just e to the x. Tack on the plus c, and that's the antiderivative of x e to the x dx. Part B. Alright, so part B, I'm going to go through the process of integration by parts again. So I look at the original integral, and I'm saying, well, what part of the original integral, if I let u equal that part, would give me a simpler function? Or what part of the original integral, if I let dv equal that part, and it's the most complicated part, I can quickly and easily integrate? And either one of those routes leads me to letting u equal x and dv equaling e to the 2x dx. Because if u is x, du is dx. If dv is e to the 2x dx, well, to get v, I have to do that little mini integral here. And the antiderivative of e to the 2x dx is 1/2 e to the 2x. I mean, remember we talked about a little formula. As an aside, we talked about a little formula for the antiderivative of e to the kx dx. That as long as k does not equal 0, we have this little formula, 1 over k e to the kx. We learned that back in chapter 6. It's helping us tremendously here in doing this example. And you're going to see it pop up more than once in this section on integration by parts. So, continuing on with this example, I write down the original integral, crank it through integration by parts, so it's u times v, that's x times 1/2 e to the 2x. I'm going to write that as 1/2 x e to the 2x minus the integral of v 1/2 e to the 2x du. Well, du is dx. And notice I can immediately, in trying to analyze this integral, I can put the 1/2 out front. And final step is integrating e to the 2x. Well, we know the integral of e to the 2x is 1/2 e to the 2x. We've already done it. So 1/2 times 1/2 e to the 2x gives us a 1/4 e to the 2x plus c. So that's the antiderivative. So to make sure you're understanding this integration by parts, I would like you all to now try number 11. So in section 7.4 exercises, try number 11. So you know the drill. Go do number 11. Pause the video. After you've done number 11, I'll be cranking through it here on the chalkboard. Okay, number 11, you were asked to integrate x e to the negative x dx. So here's how I would attack it. I'd let u equal x. dv is e to the negative x dx. That's the most complicated part of the original problem that I can easily integrate. Remember, as soon as you write down what u is, and as soon as you write down what dv is, you must compute du. Du is the derivative of your u statement, so that's just a 1 dx. You must compute v. Remember, v is the antiderivative of here, e to the negative x dx. That gives us negative e to the negative x. And then I got in the habit many years ago, and I showed you this in the previous examples, that I write down the original integral, and now I write the result of cranking it through the integration by parts formula. So the integration by parts formula, it's u times v. So that's x times negative e to the negative x. So I'll write that as negative x e to the negative x minus the integral of v du. So that's negative e to the negative x, and then du is dx. And here's what I would do, and I'm not going to write it as a separate line. I'd take this negative 1 and I'd rip it out front of the integral. So I'd have minus a negative. Minus a negative is plus. And now I finish off the problem. The antiderivative of e to the negative x, well, we know that's negative e to the negative x. And I would probably write my answer, since I have plus a negative, I'd write it as just minus e to the negative x plus c. So that's all there is to number 11. So hopefully you got it. It's time to head back to the slides and see what's next. All right, we did those two examples illustrating integration by parts, and hopefully you were able to get number 11, and it's not seeming too bad. So let's look at the next example. I mean, folks, just because we're learning a new integration technique doesn't mean we should forget about the most basic integration technique, u substitution. So in this example, I'm saying determine if a u substitution or integration by parts should be used to integrate the given functions, and then perform the integration. So in A, we're integrating the natural log x over x dx, and in B, we're integrating ln x dx. So it's kind of cool when I look at B, you know what the derivative of natural log x is, but you don't know what the antiderivative is. So once we do part B, you will know the antiderivative of natural log x. You will have a little formula, if you want to call it that, for what the antiderivative of natural log x is. But why don't we just head off to the chalkboard, do these two examples, and see how they are. Hey folks, in this example you were asked, determine if a use substitution or integration by parts should be used to integrate the given functions and then perform the integration. So let's look at A. It's the integral natural log x over x dx. So when I see this, what jumps out to me is that a basic u substitution will handle this integration problem. That if I let u equal the natural log x, well, we know the derivative of ln x is 1 over x dx. So if I substitute in, that's my u, then the 1 over x dx is du. So I'm just integrating a u du, which we know the antiderivative is 1/2 u squared plus c. Resubstitute. Boom, a basic u substitution. Part B, integrate natural log x dx. So as I mentioned on the slide, right now you know the derivative of ln x. You know the derivative of ln x is 1 over x. But you don't know the antiderivative for ln x. And that's what we're doing in part B. So when I look at part B, I'm thinking there's no way I can do a u substitution. I have to use integration by parts. So I would let u equal ln x, then dv is dx. We know the derivative of ln x. That's 1 over x dx. And then the antiderivative of 1 dx is just x. So when I crank this through integration by parts, remember the integration by parts formula, u times v. So that's ln x times x, which I will write as x ln x, minus the integral of v times du. Well, look how friendly this is. Cleaning this up, x times 1 over x is just 1. And the antiderivative of 1 dx is just x. So that's it. So here's what you know. You now know that the antiderivative of ln x is x ln x minus x plus c. We just came up with a new antiderivative formula, that the antiderivative of ln x is x ln x minus x plus c. This is something that I would file away. I would just commit it to memory. It may come in handy in the future. It's just nice to know. So you know I want you to practice one right now. So why don't you, here in section 7.4 exercises, why don't you do number 15? So you know the drill. Pause the video, go do number 15. After you've done 15, I will be here at the board working through it. All right, number 15, you were asked to integrate x squared natural log x dx. So when I look at this and I think, I'm going to crank this through integration by parts, even though I know the formula for the antiderivative of ln x, we just did that in the last example, I am not going to let dv equal ln x dx. It's going to become very messy very quickly. I'm still going to let u equal natural log x. Then dv is x squared dx. So one thing that I want to point out, when you look at your original problem, don't think the original problem that the first thing you see has to be u, and then the second thing you see is dv. I look at the whole thing. I'm saying this is u. And then the x squared dx, that's dv. So I do have it in the form, the integration by parts formula form of integrating u dv. So I just need to continue. So once I write down what u is, I have to compute the derivative du. That's 1 over x dx. If dv is x squared dx, then v is a 1/3 x cubed. So when I crank this through integration by parts, it's u times v, so that's ln x times 1/3 x cubed. I'm going to write that as 1/3 x cubed ln x minus the integral of v, so that's a 1/3 x cubed, that's v, du, 1 over x dx. So notice when I put v in here, 1/3 x cubed, I would immediately rip the 1/3 out front. So let me go ahead and do that here. So there's the rest of v times du, and du is a 1 over x dx. So just one little minor step of cleanup. X cubed times 1 over x. Well, x cubed times 1 over x, that just simplifies to x squared. And final step, the antiderivative of x squared is 1/3 x cubed. So 1/3 times 1/3 x cubed gives me a 1/9 x cubed. And that's our antiderivative. So hopefully you're able to get number 15. But I think we're getting close to that time now that we've learned a new integration technique to see how in the world can we apply this new technique of integration. So let's head on back to the slides. All right, folks, after doing those two examples, hopefully you saw, one of them, it was a basic U substitution. The other one required integration by parts. And hopefully number 15, you were able to get number 15. So it's that time to look at some applications. So remember in a previous discussion on continuous income streams, we covered the concept of rate of flow functions. And that when you integrate a rate of flow function on the interval a to b, it gave the total income produced from time t equals a to t equals b. I mean, this is the big story of integration. So again, when you integrate a rate function, it gives a total. So when you integrate a rate of flow function, it gives the total income produced. So just remember that if we have P dollars invested at an annual interest rate R that's being compounded continuously, then the present value is given by P equals AE to the negative RT, where A is the amount in the account after T years, or A is the future value. I mean, the compound interest formula as A equals PE to the RT. Well, if you take the compound interest formula, A equals PE to the RT, and you solve that for P, that's where you get the present value as being P equals AE to the negative RT. So now that we understand integration by parts, we can look at the next type of finance application, which is the present value of a continuous income stream. So if F is the rate of flow function for some continuous income stream, then the present value, P, at an annual interest rate R that's compounded continuously for uppercase T years is given by P equals the integral from 0 to T F of T e to the negative RT dt. So this looks like it's just going to be a classic application of integration by parts. So
Next up is an example. Some family, well, you should write this example down in your notes, because when I go to the board, I'm not going to write all this stuff down. But quickly, a family owns a gelateria, and it generates income at the rate of $620,000 per year. T is the number of years from now. We're going to determine the present value of this continuous income stream for the next 4 years at 5.75% compounded continuously. So we're going to have to look at all these words, and we're going to have to determine the rate of flow function, f of t, so that we can then, perform the calculus. So have this written down because I'm heading off to the chalkboard to work it out.
All right, folks, this example was an application. There were a lot of words. When I read all the words and I see something generates income at the rate of $620,000 per year, those words are telling me that the rate of flow function, f of t, is 620t. And then we want to get the present value of that continuous income stream for the next 4 years at 5.75% compounded continuously. So, here's the formula for computing the present value. In the slide I had mentioned, and I hope it made sense, but in the slide I had mentioned, you know the compound interest rate, the continuous, the formula for continuous compound interest. A is the future value, P is the present value. And I said if you solved this for P, so if I solved this for P, I would divide both sides by e to the RT. But if I wanted to take what's in the denominator and move it up to the numerator, remember that rule of exponents, I could insert a negative into the exponent. So that gives me, so in that discussion on the previous slide, I said if you took this and solved it for P, that's where this formula came from. Well, I just wanted to show that real quick. All right, so for this one, to see what's happening with this family-owned gelateria, let's see. We want to know the present value for the next 4 years. So that's integrating from 0 to 4. The rate of flow function, 620t. And then e to the, let's see, the rate is 5.75%. So that's negative 0.0575 t dt. Looks like a classic integration by parts. So what I'm going to do, so that I'm going to erase this over here, folks. I want to get an antiderivative for 620t e to the negative 0.0575t. It's a definite integral, but I want to get the antiderivative and then use my limits of integration and the fundamental theorem of calculus. So I'm just going to come over here to the side and just say, I want to get an antiderivative for 620t e to the negative 0.0575t dt. Classic integration by parts. Classic where you let u equals 620t, dv is e to the negative 0.0575 t. du is 620 dt, and v is, and that's where that little formula that you first saw in chapter 6, and I reviewed it in this video, the little formula, and quickly get an antiderivative here. It's 1 over negative 0.575. Helps if I have the correct number of zeros. E to the negative 0.0575 t. There's a t there. I know I barely got it on the board. So when I integrate 620 t e to the negative 0.0575 t dt, when I crank that through integration by parts, I get u times v. So 620t times that mess. So I'm going to write that as negative 620t over 0.0575 e to the negative 0.0575 t minus the integral of v du. So v du. Well, I could write that as negative 620 over 0.0575 e to the negative 0.0575 t dt. So putting in one more extra step, I can take this constant and rip it out front. If I take this constant and rip it out front, notice I'd have minus a negative. So that's plus 620 over 0.0575. The integral e to the negative 0.0575 t dt. So we're almost there. We just need to do that integral. The integral of e to the negative 0.0575 t, which we know, we have our little formula, we know it's going to be this. So this is that antiderivative, but because it's a negative, so there'd be a negative here. Positive times negative is negative. That's going to make this minus 620. And then I'm going to write that as 0.0575 quantity squared e to the negative 0.0575 t. So there's my antiderivative. Let me bring the antiderivative over here. Yeah, I know, it looks like a mess. So it's a negative 620t over 0.0575 e to the negative 0.0575 t minus 620 over 0.0575 squared e to the negative 0.0575 t. And I need to evaluate that from 0 to 4. So take your time in evaluating this with the fundamental theorem of calculus. If you do it correctly, you're going to get it to be 4261.224871. So the answer, because remember this was in thousands of dollars per year, so the answer, what is the present value? Since this is in thousands, I would say the present value is $4,261,224.87. This is in thousands, so when I convert it to just dollars, move the decimal to the right 3 spots, and that is the present value. I'd like you to practice one of these right now. So why don't you try number 63, and after you do 63, I'll be here at the chalkboard working through it. All right, in 63 there were a lot of words. I think it was Dina's car wash.
We were given the rate of flow function is f of t equals 2t, and we're asked to find what the present value over the first 5 years. So we have to integrate from 0 to 5, the rate of flow function, e to the negative, and it was 6% compounded continuously. So that's what we need to do. So I need to get an antiderivative for this. So just like the last one, I'm going to come off to the side to compute the antiderivative. A classic integration by parts. Let u equal 2t. dv is e to the negative 0.06t. dt, du is a 2 dt. And v is, well, we're making use of that little formula that we learned back in chapter 6. Kind of nice to know it. So we have the integral of 2t e to the negative 0.06t dt equals, using integration by parts, u times v. So that's a negative 2t over 0.06 e to the negative 0.06t minus the integral of v du. So v du, notice there would be a 2 times this. That would be in the integral. So let me rip that out. So that's a negative 2 over 0.06 that would get ripped out. So minus a negative, that'll make it a plus 2 over 0.06. Just saving myself a little space. Cutting down on the number of steps. So now we get our antiderivative. Negative 2t 0.06 e to the negative 0.06t. The antiderivative of e to the negative 0.06t, well, we know that antiderivative is, well, it's that little formula that we developed. It comes in very handy. So that's 2 over 0.06 times negative 1 over 0.06 e to the negative 0.06t. So I have my antiderivative. Let me pull the antiderivative over here. Negative 2t over 0.06 e to the negative 0.06t. And I'm going to do just a little cleanup. This product is negative, so that would make that a minus. 2 over, and then that's a 0.06 squared that would be in the denominator. E to the negative 0.06t. Evaluate that from 0 to 5, and you should get 20. I'm going to write it as 20.52. So to answer the question, I think Dina's Car Wash, I think the rate of flow function was given as millions of dollars per year. So the present value is 20, I'll say $20.52 million. All right, folks, that's it for section 7.4. So you're ready to do the homework, do the exercises in section 7.4. They may take you a little bit more time. That's okay. But go ahead, do the exercises in section 7.4, and thanks for watching.